Hi, I'm Yuan Tang. I'm from Fudan University, and it's my pleasure to give a talk on my recent research on improving the space-time efficiency of matrix multiplication algorithm. Uh, matrix multiplication, matrix multiplication and its fast algorithm, for example, the Strasson's algorithm is a fundamental computation and building block in algorithm design. However, classical two ways to parallelize the matrix multiplication has some problems. First, the classical process-aware approaches may not utilize all processes effectively unless the process number matches well the structure of algorithm. For example, the CAPS algorithm on parallel Strasson by Blood et al. Requires P to be an exact power of 7. Lipschitz et al. Improved it to a multiple of 7 with no large prime factors, that is, P equals m times 7 to the power of 6, where m is between 1 and 7, and x larger equal than 1 is some integers by a hybrid of Strassen and classical matrix multiplications. On the other hand, the communication avoiding parallel recursive rectangular matrix multiplication, the Karma algorithm by Damiot et al., assumes P is an exact power of 2, or any P's prime factor can be bounded by a small constant. So basically, the efficiency of the P approach is constrained by the number of processes and the algorithm structure. On the other hand, the classical process oblivious and cache oblivious algorithms achieve optimality either in time or space, but not both. For example, the CO2 algorithm has an odd n depths and optimal cache complexities, and the CO3 algorithm has a odd log n depths and suboptimal cache complexities. So the depth is the critical path length of DAG of the parallel algorithms. So a log n depth of CO3 algorithm is better, but its cache complexity is worse. On the other hand, the CO2 has a suboptimal depth, that is, its critical path length is much longer than the CO3, but it has a better cache complexity. So from the theory, it will be hard to tell which algorithm will perform better in practice, right? So because one is better in this way and the other is better in other way. Let's take a look at this CO2 and CO3 algorithm. You can see the CO3 algorithm is on the left hand side. So basically, at each recursive level or each internal node, we parallelize all all 8 submatrices at each recursion level, and have only the constraint that all the base case on each process is serialized, right? So basically, at each level of recursion, it's parallelize 1 n by n matrix multiplication to 8 n over 2 by n over 2 submatrix multiplications. So all the submatrix multiplications are parallelized efficiently, and they are only serialized on the base case. To enable this parallelization, it always allocates a space, such as the fifth line. The D equals the allocated size of C, right? So it always allocates a new temporary space to enable this full parallelization. So this is the reason that it incurs so many cache misses. On the other hand, the CO2 algorithm on the right-hand side serialize 8 submatrix multiplication at each recursion level by a synchronization on the 8th line, right? And the 4 submatrix on the before and after, so forms 2 parallel steps. Each parallel step has 4 submatrix multiplications, and each parallel step can parallelize all 4 submatrices, but it has a synchronization between them, right? So it has a longer depth, means a longer critical path length. And since the serialization makes the reuse of the output matrix C as possible, so that it doesn't have to allocate temporary space like in the CO3 algorithm. So it uses the memory more efficiently and has less, or in other words, asymptotically optimal cache complexities, so that it has optimal cache complexity but suboptimal depth. So it will be hard to tell which will perform better in practice by only theoretical analysis. And our contribution is to design some trade-off in space and time for both classical matrix multiplication and Strassen-like fast algorithms. So you can see from this table, our final algorithm, the star algorithm, always has a sublinear depth, means sublinear critical path length, and optimal work, and usually has optimal cache complexities as well, right? So it usually has optimal cache complexity and sublinear time, the sublinear critical path length. So it makes it better in theory, at least. Before introducing our new algorithms, I will have to give a brief introduction on our cost models and the programming models. So we use the work span model, also known as work time model. So it views a parallel computation as a DAG, directed acyclic graph. Each vertex stands for a computation, and each edge stands for some control or data dependencies. And each arithmetic operation is counted uniformly as an order 1 operation. And we count only the total work and the critical path length, which is denoted by T1 and T infinity respectively. The parallel running time will be Tp equals order T1 over P plus T infinity with high probability. This is the parallel running time for the parallel performance model when scheduled by a randomized work stealing scheduler, as the reference 3 indicates. Our memory model is as follows. Firstly, we calculate only sequential cache complexity, then relies on the randomized work stealing scheduler to yield the parallel cache complexity of Qp equals Q1 plus order P times T infinity times M over B. So the Qp is the parallel cache complexity, Q1 is the sequential cache complexity, P is the processor number, T infinity is the critical path length, M is the size of cache of each processor, B is the cache line size. So this equality is derived by the reference 1 and 37 for process oblivious algorithm scheduled by a randomized work stealing scheduler on an ideal distributed cache model. Our programming model is a nested parallel model, also known as fork-join model. So it has only 2 parallel constructs. One is parallel, the other is serial. The parallel is denoted by A parallel B, means A and B have no dependency on each other and can be fully parallelized. The serial means A semicolon B, means B depends on A, so B cannot start until A has fully finished. Now let's take a look at our time adaptive and reductive algorithm. To derive this algorithm, we have some observation on the CO2 algorithm. Firstly, it imposes more control dependency than necessary data dependency to keep the algorithm correct. For example, the auto synchronization between the 2 parallel steps is unnecessary, right? Because the multiplication by themselves has no dependency on each other. All multiplications have no dependency on each other. They should be parallelized fully. And the serialization only makes sense for later additions, right? So we remove this unnecessary serialization between the 2 parallel steps by our time algorithm. time algorithm pseudocode can be found on the right hand side. So we remove the auto synchronization between the two parallel steps, so it is the same as in CO3. All 8 supermatrix multiplication are fully parallelized. The serialization makes sense in the base case calculations. And we have two key components for the time algorithm. Firstly, the memory allocator. We can see in this pseudocode, when we recurse down to the base case, we have to calculate them independently on each processor. In order to calculate this base case, we need to allocate some temporal space of D. And our memory allocator guarantees this space for base case calculation on each processor will be reused across different function calls. So this means on each processor it may have lots of base case calculation, but they reuse the same space for those base case calculation, so that it improves the cache complexities, right? This is why we have the theorem 1 in our paper. So by our TAR algorithm, the square matrix multiplication of dimension n on a semiring will be run in odd n time, the same time complexity as the CO2 algorithm, with an odd n square plus pb square space. N is the problem dimension, p is the processor number, and b is the base case size. And optimal odd n cube over b square root m plus n square over b cache misses. Right? This cache miss is optimal, asymptotically optimal in the sequential setting, and we rely on provably efficient runtime scheduler such as a randomized work stealing scheduler to yield good parallel cache complexities. And if we assume that the base case size b is some small constant, the space bound will be reduced to odd n square plus p. Next step, we design our space adaptive and reductive algorithm, the SAR algorithm. We have some observation on the CO3 algorithm. The CO3 algorithm always allocates the temporal space irrespective of the availability of processors, right? So basically, it doesn't look into the availability of the processor. It always allocates space for all the matrix sub-MM derived from each internal node. So it allocates too many spaces. That's the problem. So our improvement is the following two. Firstly, we generalize the busy leaf property. By the busy leaf property, in one word, it means on each processor, each depth of this recursive divide-conquer has only one copy of memory. Recall that in the TAR algorithm, the base case space will be reused across different function calls, that is, across different computations, right? And for our generalization of busy leaf properties, not only the base case, each depth of the recursive divide-conquer tree will be reused on each processor. But on each processor, each depth will have only one copy of space. And this one copy of space will be reused across different function calls, different internal node, right? But it's reused, so it still saves space. This is the first optimization. And second improvement is the lazy allocation. In the original CO3 algorithm, we always allocate a space before we spawn any sub-MM. But by a lazy allocation, we allocate space after it spawns a sub-MM, and allocate space if and only if this sub-MM runs simultaneously on a different processor from the sub-MM, updating the same output region. The pseudocode can be viewed here, right? So it always still parallelizes all A sub-MM, as we see in the bottom. and we can see it has some trial lock and get lock. This is how we make the lazy allocations. And our memory allocator ensures the memory allocator is not shown in this code, but it's implemented by ourselves and ensures that on each processor and for each depth of task, different tasks will reuse the same space on each processor. So by these two optimization, we have the theorem 3, so that the SAR-MM algorithm has a sublinear time, actually a asymptotic optimum time, or the log n time, and order p to the power of 1/3 times n square space and optimum cache complexities, assuming p equals little o n. So for this SAR-MM algorithm, the time complexity is optimal and the cache complexity is optimal, but the space complexity is a little above the optimal. The optimum space is n squared. We have n squared times a factor of p to the power 1/3. So we can see the TAR algorithm removes multiplication from a critical path without using much more space, while the SAR algorithm reduces the space complexity without increasing the time complexity. So a natural idea would be combining the two and yield our star algorithm, right? So we have the theorem 4, theorem 8, theorem 7. So there are different star algorithms for classical matrix multiplication and Strasson's algorithms. So the basic idea would be a hybrid of the SAR and TAR. So the star MM Strasson is a hybrid of classical matrix multiplication and Strasson, right? There are different trade-offs between space and time. And now let's look at some experimental results. We experimented the TAR, SAR, and STAR on a 24-core machine. The machine specification is shown on the left. We can see the experimental results on the right-hand side. So we can see our TAR algorithm is slightly better than the other SAR and STAR algorithms, and they are usually better than the CO2 and the CO3 algorithms. But as we also can see that it's not significantly faster than the CO2. That's because we conjecture that the state-of-the-art memory allocator on current processor on current operating system may have integrated some degree of the memory use, but the problem is it's not guaranteed. And in our manually implemented memory allocator, we guarantee a reuse of space on each processor for each depth, and each base case calculation. So our performance is guaranteed. While if you don't use our memory allocator and use off-the-shelf memory allocators, then the performance and the space reuse is not guaranteed. That's it. Thank you.